So first talk is on light matter interaction in metamaterial by Professor Achanta Venugopal. So before to start, quickly I will let me introduce our speaker first. So Professor Achanta Venugopal obtained PhD in physics from TIFR Mumbai and PhD in electronics from Tokyo University, Japan. He worked as NDO fellow at FESTA Laboratory, Japan, and as a JST fellow in NEC Corporation, Japan during 2000 to 2004. He joined TIFR as a faculty in 2004 and is currently a professor. His research interests are nanophotonics and planar architecture for classical and quantum information processing. He has more than 130 plus journal publication. He is on the editorial board of Scientific Report and associate editor of Frontier in Physics and Encyclopedia of Applied Physics. He is a senior member of IEEE and member of OSA. He is executive council member of Optical Society of India and vice chair of IEEE Photonics Mumbai chapter. Now we are honored to have you, sir, here, and thank you for accepting our invitation and joining us today. So now I would like to hand over to Professor Achanta Venugopal to start the talk.
Thank you, Kishore and Lakshmi. Yes.
Okay, sure.
I'll share my screen.
Yes, sir, you can.
Right. I'll be talking about light matter interaction in metamaterials. So I'll make it a little bit like a tutorial. So I'll start with the very basic thing, what we look at optical properties. When light is incident on a material, so how do we, what properties do we look for? Right. So we, from the basic textbook point of view, so we know interaction of light with material. So if light is incident or applied on a, or an electromagnetic field is applied on a dielectric material, an insulating material. So we consider the force damped oscillator, harmonic oscillator model, right? So it's given by this equation here. We solve this for x as a function of time, for applied electric field as a function of time, right? So you have a nucleus to which an electron is bound, and there is, we assume, some spring constant to this. And if the electric field orientation is known, so the time dependence of the electric field is going to drive this electron motion. But because of this restraining force, so the electron oscillates, and that harmonic oscillation of this lead to x as a function of time. So from that, so we assume that, so when the electron is moving away from its static position, so we have this, the polarizability or the polarization. So because there is a dipole which is induced, so we give it in terms of this expression, n is the electron charge and x is a function of time, right? So that we can also write in terms of the susceptibility of the material, and so that comes out to be so just by getting the solution of x of t and plugging it in P and then writing the susceptibility chi, we get an expression like this, right? So this is for a dielectric, and this is known as a Lorentz model, right? And in case of metals, because these electrons are free, so we remove this restraining force term, that's omega square x term is removed or ignored. And then we get P of t, the polarization as a function of time is given by this expression, from which we can again get the susceptibility of the material, right? So from susceptibility, we can write the epsilon, the dielectric constant, that's 1 plus chi, and epsilon is known is square of the refractive index. So we know our bulk material properties, which we generally consider in defining optical materials, right? Now, if you go a little deeper, we talk about a two-level system, like an atom, right? An atom has very precise energy levels. So we consider an atom with a ground state and an excited state. That's a two-level system. And when light is incident on it, so the separation between these two energy levels can be h cross this capital omega, that's the energy difference, and h cross small omega is the photon energy, incident light field energy. Right. If we have a system like this, and this light and atom are non-interacting. Right? So then we get an uncoupled Hamiltonian, which is given by this first expression here, H0. So the first term is for the two-level system. So sigma Z is in terms of the Pauli matrices, and A dagger A or the creation and annihilation operators of a photon. If photon is absorbed, so the electron is excited from ground state to the excited state. And when the electron recombines with the hole, like it emits a photon out, and you get a photon created. Right? So this is a non-interacting term. Like, so there is no, I mean, these two independent terms are there in the Hamiltonian. But if you look at the quantum Rabi model, right? So where in addition to these two independent terms, uncoupled Hamiltonian system, when light is absorbed or interacting with the two-level system, so this third term comes into picture. Right? So in this picture, like, so this is the full Hamiltonian, which will explain interaction of a photon with a two-level system. Right? To simplify this, people use this rotating wave approximation. Here, basically, A dagger sigma plus and A sigma minus terms are ignored. Why do we do that? Like, so this A dagger sigma plus corresponds to omega, capital omega plus small omega frequency, which is a highly oscillating term. So in the rotating wave approximation, we ignore this because when we integrate the electric field over time, like, so what happens is because of this fast oscillating frequency, so the integral goes to 0. So we ignore this fast oscillating term. And this A sigma minus basically is omega minus capital omega minus small omega, which is very, very small, or if it's a resonant excitation, like it leads to a DC term or zero frequency component. Right. So under the rotating wave approximation, we get an Hamiltonian, which is known as the Jaynes-Cummins Hamiltonian. Right. So here we have the two-level system, and we have the photon component, and then we have the interacting term given by this sigma plus A plus sigma minus A dagger. Right. So as I said, like, so the capital omega is the resonance frequency of the atomic system, and omega is the resonance frequency, small omega is the resonant frequency of the electromagnetic radiation, or the energy corresponding to the photon which is incident. Right. So you can write this in a matrix form and solve for this for the two-level system, right, where G is the coupling between the coupling constant between the photon and the two-level system. Right. So omega 1, omega 2 are the two energy levels. So the ground state need not be at 0. So it's at H cross omega 1, and this is at H cross omega 2. And gamma 1, gamma 2 are the damping coefficients or the lifetimes of these energy levels. G is the coupling strength, and X1, X2 are the amplitudes, and F1, F2 are the driving forces at these omegas. Right. So now if you look at G as a function of these gammas, okay, so in the first, I mean, last 40 years, like, people have been studying this so-called weak coupling and strong coupling regimes. So here, what happens is, I mean, these terms come basically from the quantum electrodynamics QED studies, or the quantum field theoretical studies, like where the strong coupling is a strong interaction which is happening. Right. But in any case, like, so the weak coupling regime is when G, the coupling constant, is smaller than the gamma 1 and gamma 2, the decay rates of the photon and the atomic system, lifetime of the excited electron, for example. Right. And the strong coupling happens when the coupling strength G is greater than gamma 1 and gamma 2. Gamma 1, gamma 2 are the lifetimes of, or the decay rates of, or 1 over time lifetimes of photon inside the cavity, and the lifetime of the excited state electron. Right. So over the last 10 years or so, people are looking at this non-perturbative regime. So these weak and strong coupling regimes, they can be explained by this Jaynes-Cummins Hamiltonian, which is in the perturbative regime, where we ignore these highly oscillating terms, right, under the rotating wave approximation. But if you go to this non-perturbative regime, because now we are getting high intense lasers, so where you can go to much larger electromagnetic fields, and also there are ways to achieve larger Gs by having larger number of dipoles, which we'll explain briefly. Right. in short time. So in the non-perturbative regime, we have this ultra strong and deep strong coupling regimes. So here, instead of comparing the G, the coupling constant between the photon and the two-level system, right, in terms of the lifetime of the photon and cavity mode of the photon and the two-level system excited state electron lifetime. So here in the non-perturbative regime, the G is compared with the resonant frequency itself. Right. So typically these gamma 1 and gamma 2 are of the order of like 1 over picosecond, 10 power 12 of the order of like 10 power 12. But the resonant frequency, if you take a visible frequency, visible wavelength resonance, right? So that corresponds to about 10 power 15 hertz, right? Compared to 10 power 12 of gamma 1, gamma 2, like here we are talking about much larger G's, right? So the G by omega, the G, the coupling constant, is comparable to the resonant frequency itself. And when G by omega is of the order of 0.1, people said that like it's the ultra strong coupling regime. And if G by omega is of the order of 1, you go to this deep strong coupling regime. Right. So how do you study these things? So people have reported like, so basically you have a cavity, 2 mirrors, and then you have an atom in the cavity, inside the cavity. Right. Now you have omega C and omega Q. Omega C is the cavity photon lifetime, and omega Q is the frequency. Sorry, this is the frequency of the cavity, and the omega Q is the resonance of the two-level system. And G is the coupling constant, and gamma is the cavity mode lifetime, and kappa is the other one which tells about the decay rate. Right. So in the weak coupling regime, people studied this so-called Purcell effect. And in the strong coupling regime, people studied quantum Rabi oscillations. So these have been well studied over the last 40 years. Right. So this led to ultra low threshold laser single photon sources. Then you get these Rabi splittings, and you start manipulating your energy levels by this strong coupling regime. And if you go to ultra strong coupling regime, so it is expected from theory that like even the ground state is expected to be modified because of these ultra strong and deep strong coupling regimes. Right, the vacuum state itself gets modulated, so you'll have novel phenomena which you can be able to tap into. Right. So if you look at the experimental demonstrations, there are very few. If you look at the top, like, so there are very few, about like 7 different systems in which these light matter interaction studies have been done, and out of which, like, if you go to this G by omega greater than 1 or above, so there are only 2 systems here. These are superconducting qubits, and these are inter-subband polaritons. Right. So it's really still open to look at like different systems which will allow us to go to these non-perturbative regimes at room temperature, especially. So for example, superconducting qubits, like you require to operate your devices or your system in the millikelvin regime, and the same with the inter-subband polaritons, like you need to typically operate in the at least in the liquid helium temperatures. So what are needed is you need a 2-level system and you need a cavity, right? So a 2-level system if you want to design your system, light matter interaction at room temperatures, for example, so you can look at quantum dots as a 2-level system. A quantum dot is a particle in a box in quantum mechanics terminology. So where an electron is confined to in all the 3 dimensions, so that like Ex, Ey, Ez, and Kx, Ky, Kz are all quantized, right? So the size of this box, or the sphere in which the electron is confined, is comparable to the de Broglie wavelength of light. So you have quantum confinement of the electron, which leads to this quantization of the energy levels, right? So because of these discrete energy levels, like, so you have a solid state equivalent of an atom in semiconductors is possible. Right. So accordingly, like, so many atom-like properties have been demonstrated in quantum dots. For example, you get discrete optical spectra, then you get entanglement, you get like anti-bunching, like single photon emission, driven Rabi oscillation. These are all the properties which have been seen in quantum optics, in atomic systems when light interacts with atom inside a cavity. So all these things have been studied. Similar studies have been done to study the atom-like properties of quantum dots, right? So, and there's one interest in quantum dot, using quantum dots for futuristic applications is to use the electron spin inside the quantum dot because it has long coherence time. If you want to use it for any quantum measurement, is a stochastic or a probabilistic measurement. So you need to repeat your measurements many times before the coherence is lost. So the longer the coherence, the better, because you can make many measurements to get your probabilities estimated more accurately, right? So the electron spin inside the quantum dot is one such useful long coherence mechanism, or the physical physical process which you can use. So it has lifetime coherence times of the order of like microseconds. So the idea is to use a network of these quantum dots. So the electron spin inside a quantum dot is like a qubit. Information is stored in that, and a photon goes and carries information from the electron inside the quantum dot out, or carry information from one quantum dot to another quantum dot. So the network of quantum dots connected by photons is one possible architecture to look at to for quantum information processing, right? So that's to say that, like, so now you want a two-level system and a cavity. So quantum dot can be an approximation for the two-level system in a solid state. But unlike an atom which is in vacuum, so it doesn't interact with its environment, an electron or a quantum dot is embedded or in a surrounding. So it always, like, the electron is going to talk, electron and hole, they are going to talk to the environment and phonons. So it's not exactly like an atom, but it can mimic an atom in a solid state. Right. So in the cavities, like, so people use these Fabry-Perot cavities. So you have these whispering gallery modes, which have the highest Q so far of the order of like 10 power 6 and larger than 10 power 6 Q factors are possible. There's this so-called distributed Bragg reflector cavity. We have these photonic crystal microcavities, and then plasmonic localization. Plasmonic metamaterials is another area where light localization is possible. Right. So one slide is missing. I saw it at the last moment. I'm sorry. These are whispering gallery modes. So one of the used for single photon emission is a quantum dot on a ring resonator, for example, which sustains whispering gallery modes. So that's one example which is very recent, like last year report, right? So and these stacked pillared structures where you have a DBR structure. So these are basically stacks of these lambda by 4 thick alternating layers of N1, N2 refractive index materials, so that the phase, I mean, the phase is constructively adding up for light reflected from different layers, and you get like large reflectance from these mirrors, or the stack of these mirrors, right? So a DBR essentially consists of layers, multiple layers of these alternating layers of N1, N2, and then there is a layer of quantum dot in the center, and again there is another DBR layer at the top. So, and then they etch out all the surroundings to get these pillared structures, right? So this has been shown for over like 12, 13 years or 15 years or so. So, and single photon emission has been reported from these, and coupled cavity architectures have been proposed in these structures. Right. In photonic band gap materials, like, so you have again these alternating layers. So alternating layers of these refractive index lead to, I mean, in an electron inside a crystal, so it sees this, the electron is negatively charged, it sees these positively charged ions, periodical arrangement, and leads to this band structure. Similarly, in periodic alternating layers of refractive indices, so the photon sees this periodic modulation of the refractive index and leads to this band gap for the photons. So similar to the electronic energy levels, which are forbidden in a crystal, So here in a photonic band gap material, certain energies of photons or light is not allowed to transmit through the structure, it just gets scattered out. So these are the photonic band gap materials. Either you can have one-dimensional materials in which like you have alternating layers of these um, different refractive indices, or you can have these pillars, dielectric pillars in air, or you take a dielectric slab and drill holes in them, right? And these are the three-dimensional structures. This is the diamond-like pattern, or the wood pile structure, where you can stack these nanorods one on top of the other, or micro rods, depending on the frequency range. So if you have a periodic arrangement, right? So what is interesting is like, so these are dielectric rods in air. You can modify the size, shape, position, or the material of one of the rods. We can simply remove it, or we can change the material. We can change the dimension, the diameter or the length of the rod can be varied, and it acts like a point defect. Right? Now, any light, I mean, if you remove it, you can tune it in such a way that like the defect mode. So there is a defect which is created because only one of the lattice sites is being modified. It's called a point defect. So this point defect can be tuned to be within this photonic band gap region. Right. So what happens is like, so if you put a quantum dot in the center of this at the position of this defect, right? So, and light is emitted with the at the defect mode wavelength or the frequency. So then that frequency is within the band gap region for this periodic structure. So all the surrounding rods, the periodic structure is going to reflect back, scatter back the light back into the defect position. So it acts like a microcavity. Right. So just by modifying one of the rods, like so one of the lattice sides, you can make a point defect. Right. Similarly, if you want to guide light from one side to the other, you make a modify a row of these rods, so you can get a waveguide which can act like a line defect, or which can help you guide light from one part to the other part of your photonic crystal. Right. So it's possible to make that kind of cavities. Like, so this is, for example, you can start with an MBE grown, this is Stransky cross-Stanov quantum dots. These are indium arsenide quantum dots, which are capped with gallium arsenide, right? So you spin coat your resist, do the standard electron beam lithography, like you pattern holes in the resist, then you etch these holes into the, up to this aluminum gallium arsenide layer, which is called a sacrificial layer, because we can use the higher aluminum content. Like, so you have H resistance between the gallium arsenide and AlGas just by HF etching. Like, so you can remove this aluminum gallium arsenide so that you have a suspended structure. So you have air below and air on the top, and you have this very thin 100 to 150 nanometer thick periodic hole arrangement wafer is hanging, which has quantum dots inside this. Right. So people have shown different applications, including single photon emission from these structures. So these Q factors are large because of this defect creation, which is the holes are not completely periodic. You modify, basically you design a point defect within this whole array. Okay. The other one which I'll be talking about is basically the dielectrics and the plasmonic structures. So here, this is a plot of epsilon versus mu, epsilon on the x-axis and mu on the y-axis. Epsilon is the material parameter which responds to the applied electric field. This is the dielectric permittivity, and mu is the magnetic permeability of the material, which tells us like how the material responds to the applied magnetic field. In conventional materials, right, so the epsilon and mu are both negative. So these are what we see mostly around the around in nature, like so around us, like so these are mostly insulators and dielectric materials which have epsilon and mu both positive. The refractive index is square root of epsilon mu is positive. On the other hand, in the second quadrant, you see metals which have epsilon less than 0. The dielectric permittivity is negative, but permeability is positive in this case. So most of the metals and plasmas, like so, you have these materials; these are naturally existing. Similarly, in the fourth quadrant, you'll have epsilon greater than 0 and mu less than 0. You can get these magnetic microstructured magnets and split rings, which will show this kind of thing. But the interesting point is in the third quadrant, where you want epsilon less than 0 and mu less than 0. Both are negative, which leads to this refractive index being negative. Right? So metamaterials are initially considered to be negative index materials, which have unique properties, like for example, the Doppler shift will be opposite. Like, so when the source is approaching us, instead of increasing frequency as we see in n positive, so when n is negative medium around us, we see that like the frequency is decreasing, right? Instead of light bending in the way we see for a rod inside a liquid, like, so we see that the bending is in the opposite direction. So this is like counterintuitive, but these are all possible, and these do not exist in nature, but we can make these structures. But nowadays, like, so this has evolved into not just negative index materials. You can design any metamaterial where the size, the only criteria is that like the constituent, the material is made of sizes whose dimensions are much smaller than the wavelength of light. So these are some of the earliest examples of negative index materials. So you design these split rings to get mu negative, and you have this rod which gives you epsilon less than 0. This is metallic rod. So you have this split ring with the metal rod to have both epsilon and mu negative. Right? As I said, like, so the bending of light will be counterintuitive if you have negative index medium. Right? So though it started with negative index materials, nowadays metamaterials, they can be anything. Like for example, this is some hole pattern in metal where each of these dimensions are much smaller than the wavelength for which it is defined. Okay. So where does this response for these unique responses which we design come from? Right. So for that, like, so we need to understand why metal nanoparticles have different colors. So for example, if you take gold nanoparticles of different sizes, these are all spherical particles. Only difference between them is like they're all of different sizes, increasing sizes. What you see is the colors, if they are suspended in water, if you look at them, they show different scattering colors. Both the transmitted and reflected colors will be different. For example, if you take the smallest size, it's transmitted is red, but the reflected is orangish color. Right? So they have different scattering colors, both in the reflection and transmission. Right? So why does this happen? So a metal nanoparticle or any metal has large number of free electrons on the surface. Right? So when your incident electromagnetic field is resonant with oscillation of these electrons, so you have large number of free electrons on the surface. So these electrons can move up and down on the surface. Right? So when you are applying an electromagnetic field whose frequency is matching with this resonant oscillation of this resonant frequency of this electron oscillation on the surface, so you can resonantly excite or transfer energy from your incident electromagnetic field to the metal nanoparticle. Right? So similarly, if you have a metal and a dielectric planar interface to, you deposit metal on top of a dielectric or dielectric on top of metal, so you have free electrons at the surface, and under certain conditions, you can excite a charge density wave. So that is like you have a large number of electrons, so large minus signs at one position, and less number of electrons at the other place. Right? So you can have this charge density wave so that it propagates along this interface. If you look at from the basic physics point of view, when we do the Snell's law derivation using Maxwell, starting from Maxwell's equations, we look at solutions for the reflected and the transmitted components. But the same set of equations with the boundary conditions applied, if we look for a solution, like what are the conditions for which like we have a propagating wave along the interface direction, then we do get solutions. For that, the requirement is that, like, so you have a dispersion relation like this for this propagating mode, right? So which is a curve which is given by this solid line. And more importantly, like, so this epsilon 1 and epsilon 2 should be opposite in sign. If epsilon 1 is positive, epsilon 2 should be negative, and vice versa. So epsilon 1 positive means it's a dielectric, and epsilon 2 negative means like it's a metallic. So it's a metal and a dielectric is needed to have this charge density wave, and the dispersion is known. So you have some issues with the coupling of shining of light and directly exciting this plasmon mode, because energy conservation says that like, so you need the incident light. This is the light line, omega equal to ck, and this is the plasmon mode dispersion curve. So the omega of the photon and the omega of the plasmon should match for the energy conservation, and at the same time the k of the photon and the k of the plasmon should also match, which doesn't happen because there is a mismatch here in the k values. So you cannot directly shine on an unpatterned interface and you can excite these plasmons. So there are people use different techniques to excite these plasmons. These are in some sense known for a long time. In 4th century AD, they have this so-called magic cup, where you put a candle inside the cup, like it looks red in color, but if you shine light from the outside, like it looks green in color. So the reflected light is green and the transmitted light is red in color. Right. So in 1990, the first commercial biosensor based on this Krushman geometry or the prism geometry has been released. So we use this for as a biosensor for almost like 30 years now, more than 30 years, right? And you have these nanophotonic demonstrations, like for example, this is an array of 250 nanometer diameter dots, which are focusing light to a 250 nanometer silver strip here. Right. So the wavelength is around 700 nanometer, if I remember correct. Right. So this is also spacer, like the laser. This is a surface plasmon amplification by stimulated emission of radiation. So you have a gold core surrounded by sodium silicate shell, which is filled with this dye. Right. So when you shine light on this, excite the dye. So the dye emits, which will excite the plasmons, localized plasmons at the core. So you have once the localized plasmons are excited, you have very strong local field, which leads to more absorption in the dye, and the dye will emit more. So you have this amplification which happens. So this is the world's tiniest laser. So this emits at 532 nanometer, and the the 531 nanometer one is missing here, and the size of this is about, including all the core and shell, everything is about 44 nanometer, right? So even from semiconductor lasers point of view, like, so the surface emitting lasers have been patterned so that like you get nice collimated beams out, and then people also use it for biological applications or biomedical applications, including surface enhanced Raman is one good technique, where just roughen your metal surface, your Raman signals get amplified and enhanced because of the plasmon localized field enhancement. Right. So our own work, like, so we have shown for different applications. So for example, this one is a on-chip Yagi-Uda antenna. So we could enhance the magneto-optical properties of materials, right? And like this one is, for example, the bottom right corner, like, so this is a perfect absorber in which like in a very thin, like 10 to 20 nanometer thickness, like, so we can have near 100% absorption. And this has a vanadium dioxide, which shows a metallic to insulating phase transition at close to room temperature. So we can switch these pixels on and off, like, so it has stealth applications. Okay. So I'll go back to the topic which I mentioned, like, so it's basically we're trying to look at different light matter interaction phenomena. So the first one I said is the weak coupling regime, where we talk about Purcell enhancement. Purcell enhancement, or the Purcell factor, is basically the ratio of emission with and without the cavity. So that is, you have an atom or a two-level system. It's emitting some light in a free space. Now you put it inside the cavity. How does its emission modify? So if there is an emission enhancement, like, so we call it Purcell enhancement, and that depends on basically the wavelength inside the medium, So wavelength in free space is, for example, lambda 0. When you put it inside the cavity which has certain medium, so you'll have lambda 0 by n. N is the refractive index of the medium inside the cavity. Right? And if you have a cavity, like you have a quality factor, and also like you have this V, which is the mode volume, right? So you have certain mode, or in terms of easy to understand. So if you have a photonic crystal cavity, so I said like there is a defect mode, a point defect. So the point defect is going to have a local electric field at that position that has certain volume. So that volume is defined by this V. In some defect modes and some cavity modes, you may have large volume. If you have a larger volume, then mode volume, for example, so your Purcell enhancement is going to be smaller, right? You should have large Q and small V to get high Purcell enhancement, right? So this Q is in terms of the cavity mode lifetime and the cavity resonance omega 0 times tau, or in spectral domain, we measure the resonant frequency lambda and the line width delta lambda. And from that, like we estimate the Q factor. Right? This is one example of how the emission can be enhanced. So this is a plasmonic structure where a dielectric has been patterned to have a periodic grating-like structure on which the zinc oxide, zinc sulfide nanoparticles have been spin coated. Right. So what we see is like, so without the pattern, so that is unpatterned metal region, and the patterned metal region, we can compare the emission. So what we see is that like, so there is almost like 2.5 times enhancement in the emission from these nanoparticles. Right. So this is Purcell enhancement or the weak coupling example, like where the emission from quantum dots can be enhanced because of this strong local field, which is excited at the interface of this metal air and metal dielectric interfaces. So when the plasmon is excited, you have a strong local field which confines the light to nano dimensions or the interfacial dimensions. So there is another one. This more recent is the so-called noon state generation. This is a classical, non-classical state of light where whatever photons are emitted, they are all either in state 1 or in the state 2. So for example, in this geometry, we have two quantum dots which are in close proximity to a metal film, for example. So when you bring these close together and excite one of these quantum dots, this quantum dot is going to emit photon. So that is going to excite a plasmon at the interface, metal dielectric interface, epsilon 1, epsilon 2 interface. And this plasmon is going to, for example, excite the second quantum dot, right? Or it could be other way. But the main point is that the quantum dot 1 and quantum dot 2 are coupled via this plasmon mode, which is getting excited. Because of this coupling, we get, if you measure the photons, so if each one is emitting a photon out, so if you measure the photons, what we see is like these are highly directional. First thing, these are going to come in two lobes, two different directions, and all the photons are either in detector 1 or in detector 2. It's not that like one photon is going to D1 and one photon going to D2, right? So that's because of this coupling. If the coupling is made to 0, then they can come in all directions, both in D1, both in D2, or one in D1, one in D2, like all these combinations are possible. But because of this coupling, like, so we can generate these states as that like all the photons will go preferentially to one or the other direction. Right. So these plasmonic structures are also interesting for optical traps, like for example, on-chip optical traps. So we design these metallic discs and then studied silver and gold discs and showed that like, so basically gold is much deeper potential profile for trapping these atoms. So we can design starting with like which atom, which wavelength we need to trap, and then accordingly, like we can design the structure. So we measured these near field profiles and showed that like actually this potential profile exists on top of these metallic discs. Okay. So in the that's all in the weak coupling regime. So in the strong coupling regime, like, so one example I can give is in the strong coupling regime, we have this Rabi splitting or the so-called anti-crossings. So if the coupling G is comparable to the lifetime of the photon cavity mode or the lifetime of the two-level system or the excited system, then you start seeing these strong coupling features, and one of them is Rabi splittings or anti-crossings. So here, instead of this is a dispersion plot, omega versus k. So angle is related to k0 sine theta. So if this is theta, this is k0 sine theta is the momentum. K0 is 2 pi over lambda 0 incident wavelength. Right, and theta is the incident angle, which is defined here, like with respect to the orientation of my periodic pattern. Right. So here, instead of having, for example, you check this mode here and check this mode here. So instead of just crossing over, what we are seeing is they're actually anti-crossing. So they are interacting with each other, and because of which, like, so these modes are basically splitting. So instead of crossing over, they are anti-crossing. So they're influencing each other. So the energy levels are changing. Right? So this is one example of a strong coupling picture. So here I'll show one more example. This is in the Terahertz system. So this is a classical system. It's a metamaterial. So here you have a metal rod in which like we can excite a dipole. So you can have a plus maximum here and minus negative of the electromagnetic field here. So the incident electric field polarization is along this direction. So you excite a dipole in this. So this dipole is going to induce a quadrupole in these two rods. Right. So this is our quadrupole, which is excited only when there is a dipole inside this. When there is no dipole, these two rods are far apart, and this quadrupole it cannot be excited. Right. So this quadrupole acts like a continuum or a very short lifetime system, and the dipole acts like a two-level system with a finite lifetime. So when you have a two-level system, for example, with a finite lifetime, like finite line width, and if you have a continuum of system, like where all these energy levels are possible, and you have very short lifetime, so this is in lambda, like longer the broad the spectrum means, like, so you have very short lifetime, and narrow the line width means you have long lifetime. Right? When you have a system like this, like where a two-level system is in resonance with a continuum, your line shape gets modulated, and you get an asymmetric line shape called the Fano line shape. Right? So here, what we're showing is like, so initially, like, so this is a dipolar resonance. So only if you have only a rod like this, so you excite a dipole here. Right? So certain radiation is getting absorbed here. So this is as a function of lambda, and this is the intensity of light. Right? But when you have the continuum also in resonance with this, so this line shape gets modulated, and then what you see is this goes to something like this. So within this spectral drip, like now you are seeing, sorry, I'm not sure how. Okay, so basically here you will see a enhancement in transmission. So this is the so-called electromagnetically induced transparency, which is known again in atomic systems. So this is the dipolar dip, and then this enhancement in transmission is what we are seeing is because of this coupling with the quadrupolar resonance. Now, if you put another dipole underneath, right? So now this one and this one are both going to excite a dipole in this. Like, so the incident electric field polarization, right, is going to excite a dipole in the top and the bottom rods. So each one is going to induce the same field, so they just cancel out if the gap between these two is exactly the same. But if we make these gaps asymmetric, so the top gap is more than the bottom gap, for example, then you can start non-symmetric, it's an asymmetric system. So then you'll have two Fano resonances, And these two Fano resonances can also interact. And what you see is like, so one is a very broad resonance compared to the other one, like which is really sharp, right? So you can get like high Q resonances using these Fano kind of line profiles, interaction between, say, for example, dipoles and quadrupoles. Right? So in the weak coupling regime, we see the so-called electromagnetically induced transparency. So within this dipolar dip, you see a transmission enhancement. Okay. So as the coupling strength increases, right, as the G increases from weak coupling to, say, strong coupling, then what you see is splitting of the energy levels. I showed, like, so anti-crossing is one example I showed. So the other one, which is known in quantum optics in atomic systems, is the so-called Ortler-Town splitting. So here each energy level is split into two orthogonally polarized resonances. So there is a lambda upper and lambda lower. So they have orthogonal polarizations. So that's what is seen experimentally here. So here the structure is made of these split rings on a stretchable PDMS material. So by stretching, so we are slowly deforming the shape of the split ring, so which leads to scattering of the light, and these two resonances are excited. So both the modes, they split into two orthogonally polarized states. So in this also, like, I've not shown the spectrum, but here in S equal to 0.1, for example, when the weak coupling regime, like, so the stretching is smaller, so you see enhancement in transmission. And as you keep increasing the stretching, deformation of your split ring profiles, you see this splitting. So in the weak coupling regime, you have the EIT, and in the strong coupling regime, you go to this Ortler-Town splitting, or splitting of these energy levels. So in one system, you can see both of them. Right. So now we'll go to this non-perturbative regime, where we have to go to large G's comparable to omega. Like, so what kind of systems are possible? So before that, like, I'll make a detour. I'm sorry, we started late, so I'm not sure how much time I have.
Sir, 5 more minutes.
5 more minutes. Okay, then I'll skip a lot of it and go. So there are, you can have like broadband dispersionless structures. So for having broadband resonance, so metamaterials or periodic structures, once you have a periodic structure, for example, a grating, so you have 2D sine theta equal to m lambda. Right. So given the period, right, and come at some certain angle theta, and the m and lambda will define, like, so particular discrete resonances are only possible. So most of the metamaterials which are periodic are show discrete resonances or very specific resonances. But we can have broadband response structures by combining closely spaced resonances. For example, you can have different shapes. So for example, I want to get a metamaterial which works from 500 nanometer to 850 nanometer. So then what I can do is I can take square shapes of these scattering elements, covering, like, say, certain wavelength range, then circles for different range, crosses for the other range. Right? And then I randomly distribute them in an array and to get broadband response. So this is a perfect absorber, like, where we could get about 99.8% or so absorption within 10 nanometer silicon layer. Right? So the other way is to go into these quasi-periodic structures. You take the same number of scattering elements. First, you arrange in square lattice. You look at the Fourier transform. It shows discrete points. The Fourier transform of a square lattice is square. But if you arrange the same number of dots in a quasi-periodic pi by phi symmetry fashion, and you look at the Fourier transform, it gives a very dense K space. So that means for a given K, right, you can have different orientations. So there is no polarization dependence, and you also have multiple magnitudes of Ks which are possible, which means, like, K is 2 pi over lambda. So eventually, like, you can get a broadband spectral response out of this. Right. So we demonstrated such structures where we showed that, like, because here you can get almost like 3 orders of magnitude enhancement in the local electric field. So you can generate second harmonic. So the nonlinear properties are also possible in this. So they have M and K values very similar to the bulk unpatterned metal, but they have very unique. So they have very broadband response, right, which is polarization and launch angle independent, and generates nonlinear properties, nonlinear harmonics. Higher harmonics are also possible to be generated using this. These structures have very unique near field patterns. So for example, you see this pattern here, the plasmon mode is propagating like a topological pathway, like so it's propagating along this direction, right? So these are interesting for hot carrier studies. So when the plasmon is excited, like so the plasmons have a short lifetime of the order of like picosecond at the most, because they interact with, they scatter with lots of the sea of free electrons which are inside the metal, right? So but then what happens to them? So these are high energetic, so they're exciting with certain energy, so they are going to generate hot electrons or high energy electrons, energies which are larger than the Fermi energy, for example. So people said that like, so it has a large number of applications using, I mean, involving catalysis, right? You can have local doping and other things. So the basic question which we can ask is like, so how does this hot carriers, plasmon to hot carrier conversion take place, right? So we studied this using pump probe techniques and showed that like actually the bulk band structure of the gold matters, right? So we did the pump probe measurements and showed that like, so you can have scattering into different valleys which are possible, and interfering pathways will lead to different pump fluence dependencies in the decay times. So we can also fit these temporal profiles to get all the time scales which are involved in each of the process. Right? So there is another way to measure plasmon lifetime. I'll skip this. It's basically Gauss-Hanschen shift. So so in case of plasmons, when you excite plasmons, they propagate along the interface and then couple to the far field. So if you look at the incident field, the centroid of the incident field and the centroid of the reflected beam, so you see that like, so they're shifted in space, right? So the plasmon mediated Gauss-Hanschen shift is because of this plasmon propagation. So because the plasmon lifetime and the inverse of the line widths which we measured, they match pretty well, showing that like, so basically the beam shift is proportional to the plasmon line width, right? So this is interesting because if you have a periodic grating, right? So when you launch light, so you see that like basically the short pulse is getting distorted. So there's a chirp in the pulse. But here, if you have a broadband structure, so the chirp is not there. So the entire pulse can be reflected from these surfaces without any distortion. So once you have this periodic structure, it's quasi-periodic structure. So we showed about like 120, 130 times enhancement in the transmission of light through this. So you shine light from here and you measure the transmitted intensity and compare it with the unpatterned gold metal transmission. So compared to the unpatterned metal transmission, you get about 130 times enhancement in the transmission at the peak. Right? So once you have this, what it means is you have very strong plasmon excitation. So you have very strong local electric field because of the plasmon excitation. Once you have this, you can look at, for example, quantum dots on top of the structure. You see that like, so there is a shift in the PL emission, right? So you do the time resolved measurements, put in all the factors and do the complete Rabi model calculations, and you see that you have these Rabi oscillations, the flopping of population from between different energy levels. And you see that, so basically one possibility is that like you have large number of hotspots on your plasmonic quasi-crystal. So if you have a bunch of quantum dots here and a bunch of quantum dots here, they can interfere with each other. They can interact with each other through the plasmon excitation. So this emitted light is going to excite plasmons at the interface, and then they talk to the bunch of these quantum dots which are here, right? So that could lead to these long coherence times which are possible in this system. Okay. Just to summarize, like, so light matter interaction in metamaterials would be useful to cover all the four regimes, both perturbative and non-perturbative. You can use them for different applications, and These are the people who are involved in this work. All the ones in blue are currently in the group, and the blue here are the theory collaborators which collaborate with. And this is my email ID. If you have any question or query, please do write. Thank you.
Thank you, sir. So now for the audience, QA session is open. So please put your question in the QA box. Sir, we have a couple of questions in QA session.
Yeah. So the first one, of course, the refractive index is negative is possible when both epsilon and mu are negative, n is negative. And people have demonstrated this, including perfect lens or near perfect lenses. So when, yeah, it's possible. Can you please explain about the plasmon mediated hot conversion? Is it related to hot electrons? Yes, I mean, they're basically hot electrons compared to the Fermi energy. They're like, so basically we are exciting a plasmon, right? So this plasmon energy can be high up in the band. I mean, compared to the electrons, like these plasmons can be higher in energy compared to the Fermi level. So these plasmons, like they convert to high energetic electrons. So they are the hot electrons basically. Right. So the conversion happens because initially it's a charge density wave, which is converting all these electrons which are involved in the charge density wave. So they are going to convert to hot electrons. So that hot electrons are mediated by the scattering with the electron cloud, which is in the metals.
One more question is
this is how photonic band gap of multi-layer metasurface is calculated. So there are techniques like finite difference time domain. Then you have finite element methods, right? So if you have freeware, like you have MEEP, which is the MIT software, so which can be used for calculating the band structures, or there are commercial as well as free softwares available to do these. Basically, they solve the Maxwell's equations and then calculate the band gap. The band gap, specifically band gap solvers are available, right, which use the block periodicity conditions and then calculate the band structure.
Let me again thank Professor Achanta Venugopal for this excellent talk and for accepting our invitation. Thank you, sir.